In this video, we'll cover the problem, get perfectly sized friend groups. We'll talk about what the question is asking. We'll go through some pseudocode of how we can approach this solution, and then we'll actually code it out. So, in this question, we'll be given quite a few inputs. We'll have our graph, which you can see on the left-hand side of the screen. This is our example graph. We'll also be given a friends array that contains a bunch of strings representing the various people who are friends in our graph. These will all be strings. And just to keep things simple with this example in terms of space, I have given every friend a one-letter name. So those are two of the inputs. You'll also be given a lower bound and an upper bound here. And in this question, we are defining a perfectly sized friend group as a group whose size fits between the lower bound and upper bound. Both of those are inclusive. So as an example, in this problem, if you had a friend group that had 2 people, it's considered perfectly sized. If it had 3 people or 4 people, those are all considered perfectly sized. But if it had 0 or 1, or maybe 5, 6, 7, or continuing onwards, those are all considered not perfectly sized friend groups. So, the output in this problem should be the number of perfectly sized friend groups that are present with the inputs that are provided. So, to start with this question, let's think about how would we solve it if all we wanted to do was count the number of friend groups, period. We don't have to worry about anything related to being perfectly sized yet. Well, we already know how to do that, right? We would just traverse through all of our friends, and every time we hit a friend who we haven't visited before, we're going to bump our count and then go mark that entire portion of the graph as visited. So as an example, if we hit the A node right here, then what we would want to do, like right here, let me put an arrow. This A node, we would come here and say, all right, mark this whole portion of the graph as visited so that we never visit it again. And then you just continue onwards. So when you hit D right here, I'll put another arrow, you would see, oh, it's already visited. I don't need to increment the count, and you would just move on. That's the standard way to count the number of friend groups that are present in a graph. Let's think about how we can sort of modify this solution that we have to meet the requirements that we have here, which is that we should only count groups that fit between our boundaries inclusive. Well, really what we need to do is we need to know how big a group is. So this idea of we don't want to count the same group at A and D, that's still present, right? Because let's say if we consider this CHG group on the bottom left portion of the screen, if we count it once for the C node and then again for the H node, that's not correct. Even though this group is a perfectly sized group that is only of size 3, we only want to count it one time because the output for this question should be 2 because we have this top section F and B and this bottom section of the CHJ. So we still want this concept of tracking visited nodes and making sure not to revisit a portion of the graph. The only difference is previously we just said whenever you traverse a subsection of the graph, bump the counter. But now we want to make sure, hey, only bump the counter if this is perfectly sized. So the way we want to handle this question is we need some way to figure out the size of a particular portion of the graph. So let's start pseudocoding this out, and then I will talk about how we can actually figure out the size of a portion of the graph. So we know that we need to iterate through our friends array. So let's just say iterate through friends. And you can imagine that we would have a visited set or array, kind of depends how you want to do it, but some sort of way to track nodes that we visited already. I'm not going to explicitly write that, but of course that's required. Okay, so we iterate through each friend, and for each friend, what do we want to do? We want to say, if it's visited, we just skip it, right? We don't have to do anything because that node has already been taken care of, and we don't need to do anything. So let's just say skip. Otherwise, so at this point, we could sort of assume that this node has not been visited. We want to say, get the size of this group, of this friend group. So let's say get size of friend group. And then here, we're going to say, if the size is perfect, then bump our counter. That's the core of this algorithm. then bump. Then we'll just say, for simplicity, let's just say count plus plus, just to say we're incrementing whatever our count is by 1. We probably won't name it count, but just for simplicity here. So really the tricky part and what's new here is how do we get the size of a friend group? Well, we know that we are processing, let's say, this entire portion of the graph at once with a BFS in order to mark the entire portion as visited. So the question becomes, can we tweak our BFS so that it can also tell us the size of the friend group while also marking that whole friend group as visited? And what we've seen many times so far is the key piece that changes between a BFS implementation is the step where you process a node, right? It's the logic that you apply to every node as you traverse it in the BFS. We know that inside of your loop, the first thing you do is you remove a node. That's pretty standard. Then you process it, which we'll come back to in a second, and then you add children or neighbors onto the queue. But that processing step determines what do you do for every node. Maybe you want to print the node. Maybe you want to add the node to an array. Maybe you want to check some condition and then add the node to an array. It kind of varies between problems. So for this problem, we want to figure out how can we modify the process node step so that we can also return the size of a given cluster or friend group. And the way we do that is we can actually just have some sort of counter that, let's say, is like the size of the friend group. And for every node, we just want to say, I won't say count plus plus because we've already used that here. So let's just say size plus plus. Just to say that we're incrementing the size of this graph. So you can imagine if we handle this first subsection of the graph here, right? We would start at the A node, the A friend, and we would be here. And we would say, all right, we're processing the A node, bump our counter. Let's just write it here as 1. Then you add all of these neighbors or children to the queue. So we add D, I, E, and G. We go to D first. We say, oh, bump the counter. So now it's not 1, it's 2, our size. Then we go to I. We say, okay, bump our size. So it becomes 3 because we've now handled the A, or let's not draw it like that. We've handled this node, the A node, the D node, and the I node. Then we go to E and we bump our counter to 4. And we've handled this node now. And then we go to G and we bump our counter to 5. And now there are no more nodes. So we've just figured out the size of this friend group is 5. And we can return that back out of our BFS. And then right here, we'll check, hey, is it perfect? Is it between our lower and upper bounds? So this is really the key modification to the BFS strategy that we have to make in order to make sure that we only count perfectly sized friends groups. All right, now let's talk about the complexity of this solution. So the very first thing we always want to do when we're doing our complexity is we want to define our variables. Let's do it on the right-hand side for the sake of space. So let's say V is going to be the number of vertices or friends in our graph. Remember, vertices are the same thing as nodes, and in our case, that's the same thing as friends. We also want E, which is going to be the number of edges in our graph. Okay, so we know the time and space complexity of a standard BFS, and this is not going to be too different, right? We have our normal BFS is going to be O of V plus E time and O of V space. I'll go ahead and write that first, and we'll see after that if this question is any different. But we know that it's O of V plus E time in a normal BFS, because every node needs to be added to the queue, so we have to have a V there. And for each node, we explore all of its edges, which means that in total, we explore all of the edges in the graph. So we also have that E there. In terms of our space complexity, we've discussed this a few times, but if you have a graph that looks like this, and your start node is this middle node right here, then you can imagine that after we process the start node, the middle node, we would add every other node onto the queue, and we would have V minus 1 nodes in our queue at one point in time. So that's O of V minus 1 space, which is just O of V. Okay, so that's a standard BFS. We know that. Now, if we look at the extra logic, we're iterating through friends here. That's just going to be O of V time and O of 1 space. It will be time because we're iterating through every friend, which is each of our texts. So that doesn't affect our complexity. This right here is just a simple check. It's constant time. This is the same thing. So that doesn't matter too much. The other question is our BFS different because of our change? Well, not really. We're just tracking some variable, and at each iteration, we are incrementing it, so that's constant time. So our standard BFS, time and space complexity, is accurate for this question. Okay, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've imported our queue. We have the example input and output right here that we discussed in the approach. I've also set up the skeleton of our function with the 4 parameters, and I've written a simple test here so that when we're done, we can make sure that our function works at least on the example. All right, let's get into coding this. So we know the very first step when you're given an array of edges like this is you want to build a graph. So let's do this the same way we always have. Let's just say build the graph using our friendships, because that is the edges array that we're given. This won't be anything too fancy. We've seen this before, but we'll create graph, which is an empty object, and we'll return that in the end. In between, we want to iterate over every edge and grab out each of the nodes from that edge. So like here, we would grab out E and G, and we want to say graph at node 1 dot push node 2. So we're saying, note down the fact that from the E node we can go to the G node, and we need to do the opposite direction. So we want to say we can go from the G node to the E node. This is what's important with an undirected graph, is you have to get both directions. We also want to handle the case where either of these are undefined, and just make sure that we set them to an empty array. So we can say if not graph at node 1, then set graph at node 1 to an empty array. We can fix this, and we can go ahead and use Command D here to change both of these at once. Okay, so that should build our graph for us. Now we've got that out of the way. The way we said we were going to handle this problem is that we want to iterate through all of our friends and just check each person who hasn't already been visited. And if they haven't been visited, we get the size of their group and potentially bump our counter. So we definitely want to have this counter. We'll call it num perfectly sized friend groups. Quite a long name, but that's okay. It's rather, I prefer it to be overly descriptive as opposed to short, but maybe not clear. And let's go ahead and create our visited set too, because we know we're going to need that. Visited is going to be a new set. I'll just move it here. All right, now we want to iterate over all of the friends that we have. So over friends.length, I++, and we can say the current friend is going to be friends at I. Now here, what do we want to do? Well, we said if the person is already visited, we should just skip them. So we can say if visited has this friend, just go ahead and continue. We don't need to do anything. Otherwise, we want to get the size of this current group, of this current friend group. So let's say current friend group size is going to be, and let's write a function. It's going to say get friend group size. So this is where our BFS is going to come into play. And we'll talk about what arguments that'll need in a moment. So we've gotten the friend group size. Yeah, so now we want to check that it's a perfectly sized friend group. So we know that it has to be greater than or equal to the lower bound and less than or equal to the upper bound. So let's check that condition. If it's less than or equal to greater than or equal to the lower bound and is less than or equal to the upper bound, then we want to increment our counter. And that is the core logic here. We want to make sure that we return our non-perfectly sized friend groups in the end. I believe this should be the core logic of this function. So now let's go ahead and talk about this get friend group size function, which is where a lot of the interesting work happens. So first of all, it's going to take some parameters here. So what does it need access to? Well, we need to know what friend we're currently on. That's sort of our start node of the BFS. We need the graph so that we can figure out, who are the neighbors or children of the current node. And we need this visited set so that we can know which nodes have already been visited and update that. I believe that's all we need, and if anything else is needed, we'll figure it out pretty quickly. Okay, so when we come in here, really there are two goals that we have. Number one, Number one is mark all nodes in the current group as visited. And number two is to calculate the size of this group. Let's focus on number one first, since we've kind of seen how to do that before. So we know we're going to use a BFS to traverse the entire portion, this portion of the graph. So we'll create our queue, which is going to be a new queue. We'll go ahead and add our start node, which is going to be the current friend, onto the queue. We'll say iterate so long as the queue's size is greater than 0. We want to grab out a node by just dequeuing like this. We'll process the node, which we'll leave and come back to. We want to grab the neighbors of this node. We can call it neighbors or children. Just to mix things up, I'll say neighbors. It's going to be graph at that node. And that's the whole purpose of the graph, is you can pass in a key, which is a node, and it'll tell you here the neighbors or children of that node. We have to handle the case that this evaluates to undefined. Maybe that node has no neighbors. So if that's the case, let's just go ahead and continue. We don't want to do anything. Otherwise, if there are neighbors, let's iterate over each of them and add them to the queue. The one thing is, we don't want to add a neighbor to a queue if it has already been visited. So let's just go ahead and say, if not visited dot has the neighbor, then let's add it to the queue, like this. So to be clear, what I'm saying is, if the neighbor has not already been visited, right? Because if visited dot has the neighbor, that would return true if this neighbor has been visited. And if it returns true, then we want to flip this so that it's false and we do not add to the queue because we've already visited that neighbor. So all I'm saying is only add unvisited nodes onto the queue here. Okay, so this is the skeleton of our BFS. Now, we're still focusing on part number one, which is that we want to mark all nodes in the current group as visited. So to do that, in our process node step, all we want to do is for every node, when we process it, we just want to say, hey, this node has been visited. We don't need to visit it in the future. So it's very simple. We can just say visited.add the current node. That's all we need to do. All right, so this covers goal number one. Now let's modify this so that we also get goal number two. So we want to say, we need to have some sort of count. So let's say friend group size is going to be 0. And let's make sure we don't forget to return that value in the end. Now, every time we hit a node, we want to bump our count because every node increases the size of our group. We know that we're tracking visited nodes, so we should never touch the same node twice. As a result of that, it should be totally fine to just make sure that at the process node step, we're always bumping our counter, because this will only happen once per node. Once it has been visited, and we'll add it to the visited set right here, it will never be added to the queue again, and we will never hit this line again. So, with that logic in place, this function should take in a current friend who has not been visited, and it should go ahead and figure out the friend group size of that group and mark that whole group as visited so that it's never traversed in the future. Then over here, when we hit another node who is in that group that we've already explored, it should be skipped because of this line and will never go into our BFS to begin with. So we've written quite a bit of code here. Let's go ahead and verify that it actually works. So the output should be 2. So let's go over to the terminal. And you know what? Okay, there. Now the whole thing should be visible. We can clear that and run it. And we get 2 as our output. Great. So it's looking like this works. Let's also go ahead and write out the complexity of this solution. So we can do the time and the space, but before that we want to define our variables. So v is going to be the number of vertices, which is also the number of friends. E is going to be the number of edges, which is also equal to the number of friendships. So our time complexity is going to be O of v plus E, and our space complexity is going to be O of v. to see our time complexity, we know that we know the BFS is going to be O of V plus E. We've kind of seen that before. But the basic idea is that every node will be added to the queue one time, and for every node, we're traversing all of its edges, which means in total, we touch every edge. So we have a V, we have an E. This function, the only thing we're doing that sort of depends on any of our inputs in terms of how much work we do, is this loop right here. We're iterating through all of the friends, so that's just O of V again. So the overall time complexity is O of V plus E. For the space complexity, the reasoning we've handled before still applies here, which is that you could potentially have almost all of the vertices in the graph on the queue or inside of the queue at one point in time. So that gives us O of V space. Also, this visited set, after we're finished traversing, should hold every single vertex or node in the graph inside of it. So that's another reason for this question to be O of V in terms of the space complexity. All right, that's all for this video, and I'll see you in the next one.